The James Webb Space Telescope is an infrared observatory that aims to complement and extend the Hubble Space Telescope with the ability to see longer wavelengths coupled with greatly improved sensitivity. Planned for decades with budget overruns and a rolling launch window, the next generation space telescope launched on Christmas Day last year and spent the first month of its service life reaching Lagrange Point 2.
And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Today, James Webb's Deputy Project Scientist Stefanie Milam beams in to discuss this important next step in studying our universe.
This is a Trekzone conversation.
Well, Stefanie, thanks for beaming in. Can you tell us a little bit about your role there at the Goddard Space Flight Center, please?
Absolutely. First, thanks so much for having me. I am the Deputy Project Scientist for Planetary Science on the James Webb Space Telescope. What that means is my job was to make sure this extremely sensitive, large space-based telescope that's designed to detect the first stars and galaxies of the universe can actually do things a little bit closer to home. So we want to study objects in our own solar system as well as planets around other stars. This proved to be a little bit challenging, so I was brought on to help make sure that we had enough justification to enable these capabilities, as well as work with the project to make sure that they were actually doing the things that we needed them to do.
Well, very, very cool. Now, Stefanie, we've seen in the last week these images of the mirror alignment and even a selfie after an incredible journey to Lagrange Point 2. What's the feeling like there in mission control?
I get to say that I was one of the first people that was on shift working at the Space Telescope Science Institute in our operations center when these photons of light from the universe came through the James Webb Space Telescope down to Earth. It was absolutely exhilarating to see the excitement of the instrument teams, the project, everybody that's been working for decades, finally getting to see light from the universe through the eyes of the James Webb Space Telescope. It was really an exciting experience. And, it's step one on the whole process of getting this telescope commissioned.
What I think is incredible, people from the outside looking in see a fuzzy image, a blurry image, but that aside, just the fact that this telescope has traveled so far, done so much, spent so much time being developed, it is that incredible achievement to say, hey guys, I'm alive and I'm here, and we just need to fine tune everything, and then we can start peering back into the universe. Absolutely.
Even though they're fuzzy and it's a scattered mess of dots, it meant to us that the telescope is actually working. It meant that the instrument is working, and it meant that we can actually see things in the universe. All the steps from here on out are merely tweaking the telescope, getting it in focus, making sure all of those 18 little dots scattered sparsely across the screen are aligned up to make one single star. We have to make this telescope, each one of those 18 segments, act like one single mirror. And so that's an iterative process, but we've practiced it, we've rehearsed it in space-like conditions before we even launch the telescope. So this is something we know how to do, and we know how to make the telescope work from here on out.
And so, aside from the alignment, is there much more to do before being able to do some serious observing?
Yes, so we actually have another handful of months worth of work to do. So the alignment of the mirrors themselves, as well as making sure all the optics are proper to do science, takes a couple of months. As I said, it's an iterative process. We have to basically move one of the mirrors, make sure that star that we believe, or the light that we believe that's associated with that mirror, moves in the right way. And then we tweak it, we align them all so that all the stars align up into one. That's a very iterative process. And that's the first step. Then we actually have to align the optics with each of the science instruments that we have, the heart of the telescope. We have 4 science instruments, and they're all behind that primary mirror. So we have to make sure they're all sort of aligned as well. And that's sort of what we were seeing with that initial selfie picture, was one of our science cameras was actually taking a picture of what the light looked like projected onto that camera itself. And so we have to do that with all 4 science instruments to make sure everything's properly working. Then we have to actually commission the instruments themselves. We have to calibrate them. We have to make sure all their modes work, that we can actually observe different types of objects, that we can observe in different manners. All these things come into play before we can start our full science operations.
Well, is there a priority list once we get everything organized and everything's aligned and the telescope is fully operational? Is there a priority list of objects to study?
Not really a priority. It's sort of first come, first serve. It's whatever's in the sky that we can observe. So we already have our first year of observations scheduled in a database ready to be scheduled. And that scheduling depends on when those objects are actually observable from the telescope. So we can only see certain parts of the sky at certain times. And so all those objects get sorted by when we can actually see them in the sky. And then the priority goes to, we have one program in particular that's called the Early Release Science Program. So this was allocated time from the director of the observatory to take observations in different ways of different types of objects to release to the science community with no proprietary period whatsoever, so that the science community can have data in hand ready to go so that they can prepare observations for the next year of science. And so those get a little bit more priority, but again, these objects still have to fall within, when they're actually observable with the telescope.
Well, time on the telescope will most definitely be at a premium. So even before the mirrors are aligned, is there a wait list for those astronomers? And how does it all work? Who decides who gets priority and time on the telescope?
Actually, we decide. Astronomers decide. The entire scientific community, our peers, are the ones that decide which science gets prioritized for the James Webb Space Telescope. So as I already mentioned, we have our first year of science already allocated. What happens is every year, the Space Telescope Science Institute releases a call for science proposals. So you come up with your most brilliant idea of how to use the James Webb Space Telescope, be it to, search for another Earth-like planet, be it to study comets, be it to search for the first stars and galaxies of the universe. Whatever it is, you have to write a scientifically compelling proposal. These all go into a stack of proposals that are then distributed to a committee that is established from the scientific community itself. So these are our peers that are pulled from the community that volunteer their time to review all of these proposals, rank them in scientific priority. Once those are ranked, we then come up with a final list based on just the amount of time that we have in a given year to observe, and that time is then allocated to those higher prioritized programs. Anyone in the world can propose to use the telescope as long as you have an affiliation. So, even if you had your most brilliant idea, you should think about writing your proposal next year.
The one thing I've discovered on Talking Science is that it's not just about astronomy and astrophysics and discovering these things. It's about writing proposals, be they grant proposals or time on a telescope proposals. There's a lot of selling yourself that goes into this, and one thing that I think should be covered in a unit at university or college.
Yeah, absolutely. We spend a very large amount of time justifying our work to our peers and our community, our funders. So as a NASA scientist, I'm supported by the general public of the US community that pays their taxes. And so the taxpayers are the people that pay me. They're my boss, right? So I have to tell them the kind of science that I'm doing and hope that they appreciate it in some level and continue to support the NASA funding system for the science that I do.
Well, Stefanie, James Webb has been in development since the late 90s, with construction commencing almost a decade ago. Now, we've spoken on Talking Science about how it gets to a point in the design process where instruments and technology need to be locked down. So has there been any further advances since that lockdown point for Webb that you wish could have been included?
Well, absolutely. So I've been working on the James Webb Space Telescope for about a decade now. And as I said, I was brought on as the person to make sure this telescope can do solar system science. And so there were capabilities that I really wanted to make sure the telescope had, just so that we could do more science. But some of those things were already locked into place well beyond when I even started my position. And so there were things that I had to actually learn how to use and to work around. So instead of going a direct route, if I was designing a telescope from scratch, or if I was given any options that I wanted, the full package on a new car kind of a situation, I would have had much more direct ways to do the science that I wanted to do for the solar system. However, that wasn't my option at the time, because we were already well into the instruments being delivered and things starting to come together by the time I started on the project. So learning how to work around what was already designed and implemented was definitely something that I had to do. I will say, though, one of the funnest challenges that the James Webb Space Telescope had was when it was first conceived and first designed, exoplanets weren't really a thing. And maybe one of them was believed to be known, or the first observation had happened, but it wasn't really a big thing. Now we know there's almost 5,000 planets around other stars today. And we knew well into the JWST project, especially after design and implementation, this was something that was going to be big, and we had to make sure the observatory could actually observe objects around other stars. And so having the instrumentation upgraded in a way that we could actually do exoplanet studies, things like coronagraphy, transit spectroscopy, was something that had to be added to the instrumentation and the design of the telescope. And that was sort of the final upgrade that happened. Beyond that, the final upgrade that happened was implementing tracking targets that move across the sky in our own solar system. So being able to move this extremely sensitive, large telescope in space to track something like a comet or a near-Earth asteroid is really hard to do. I mean, it's a giant boat, for Christ's sake, And so making it move and slew across the sky was something that was really challenging. And so implementing a mechanism in place and software, really, that we could actually be able to do something like that was something that came into play to enable solar system science.
Well, let's jump back to L2, Lagrange Point 2. It's a spot in Earth's orbit where the gravitational forces of the Earth and the Sun are in balance, around 0.01 astronomical units away and trailing the planet. Now, that in and of itself is a tricky mouthful, and I've been diving into orbital mechanics researching for this question. So what exactly does all of that mean, Steph, and why is it a good home for James Webb?
It's the perfect place for us to actually have an infrared space telescope for multiple reasons. One is because we have an infrared telescope, so we're extremely sensitive to radiation that's coming from the sun, but also the Earth and the moon. So being somewhere where we can actually protect the observatory with our large sun shield, keeping all of that on the sunward hot side of the observatory, is something that really helped enable this observatory to be such a large telescope. So we're 1 million miles away from Earth. We can always point towards the sun and Earth on the sunward side and protect everything on the observatory side. The telescope mirror and all the instruments are always in the shade, and that's really key to having the sensitivity that we need for this telescope. Additionally, we at this certain point, and it's not a point, it's a well, so it's not like an actual stable gravitational point. We still do have to maintain staying within that point, but we don't have to fight near as hard as if we were floating somewhere in free space. So that helps us save a lot of fuel by staying in this gravitational well, such that we can follow the Earth around the sun. But also, so by saving fuel, that means we have a longer mission lifetime. But also, we have this access now to Earth and the sun all the time. Earth for downloading our data, which is critical for any kind of science, as well as controlling the observatory, but also to the sun so that we can power the spacecraft itself. So it's really a critical place for us to be. We don't have to maintain the telescope whenever it's going around Earth orbit, for example. That way it's near the sun at some point. We have limited access to the sky if we're in Earth orbit. We always have 24 hours a day access to the sky, which is fantastic. And we're in a nice, cool spot where we can have a nice long lifetime and not have to burn as much fuel.
And I would be remiss in not pointing out a bit of an Aussie connection with James Webb. Obviously, being a million miles away, you're relying on the NASA Deep Space Communication Network to hear from James Webb and talk to James Webb as well. And of course, that's our good friends down at Tidbinbilla being part of that trifecta of the Deep Space Communication Network. Absolutely.
And we are 100% reliant on the Deep Space Network to download our data as well as upload commands and control the spacecraft.
Well, Stefanie, I cannot wait for the exciting discoveries laying in wait for James Webb and your team there. It's going to be very, very exciting. Getting those mirrors aligned, getting the observing happening. Good luck with all of that. And thanks again for beaming in to Trekzone.
Absolutely. Thank you so much for having me, and looking forward to our first science results.
Bye.